Hello, everyone, and welcome to today's webinar, which is about a rather interesting and lesser known aspect of gravitational physics, which is alternative models of gravitation. First and foremost, I would like to extend a warm welcome to our guest speaker, Mr. Christian Oslapas, American Lithuanian jet pilot and NASA vs. JPL Solar System Ambassador, who, having formerly trained in astronomy, aircraft systems, and earth science, has been involved in citizen science research projects with NASA JPL, the European Space Agency ESA, and the Laser Interferometer Gravitational Wave Observatory, better known as LIGO. He is also a scientific advisor and science education representative at various reputed organizations. We welcome you, sir. As already mentioned, we'll have a short representation, then a question and answer session where you can put your questions in the chat box and we'll handle it from there. Also, one important notification is that at the end of the session, we'll share a feedback form in the form of a link in the chat box to you, which you have to fill up in order to receive your certification. Over to you, sir. The floor is now yours.
Thank you so much for that introduction. Thanks. Really grateful to be here. Yeah, like she said, just finished my master's degree in astronomy, and it was a lot of work. But it's been a lot of fun. I live in Salt Lake City, Utah right now, and my area of specialty was gravity, but also did a lot of things in observational astronomy, and it's been pretty great to use telescopes and look out at space. So anyway, I'd love to get started here. So what I was kind of hoping to do today was talk a little bit about the history of gravity and then move on to some of the newer models of gravity that challenge some of those historical models. So a long time ago, about 384 to about 322 BC, we had Aristotle, the ancient Greek philosopher, and he had many different ideas about the universe, and one of those was about gravity. One of his reasonings about gravity was that different elements attract each other. So for example, if you have water, water would attract water, or air would attract air. And this idea made sense because usually when you see water, you see it in an ocean or a stream or a river. It's usually together. And when you see air, you see it all together. So his idea kind of made sense. However, there were some problems with that. For example, one experiment to easily test this is you shoot an arrow, like a bow and arrow in the air. And if his ideas were correct, the arrow would immediately go to the ground. But instead, of course, what you see is the arrow will travel a certain distance and then fall to the ground. And so they had a lot of problems with actually experimenting on this. And they had to come up with all sorts of confusing, different ways to try to explain this. And so one of the ways they said is, okay, well, maybe the arrow creates a vacuum around itself, and then air attracts air, but then eventually it dissipates. So Samar's asking if he wants to put the slides. So yeah, if you want to put the slides up, you absolutely can. Let's see here. Thank you for that, by the way. And if you are running it, then I can just say, I'll just say next. And if I can move it, then I'll move it. But so you can go to that next slide there. So this is just the picture of Aristotle, who we were just talking about, that ancient Greek philosopher. You know, even though his ideas about gravity were not correct, they persisted for a really long time in history because he was a smart person. He had a lot of great ideas. However, they just did not hold up to experimentation. And then if you go to the next slide there. So the next kind of person in history who you know, as far as in Greek history, talked about gravity is Ptolemy. And so he lived from about 100 to 170 AD, so just a few hundred years later. He did teach that the Earth was spherical. One of these misconceptions is that we think, oh, for thousands of years we thought the world was flat, and not all people thought the world was flat. That is absolutely not true. Ptolemy, for example, that's about 2,000 years ago. He taught, and many people accepted, that the Earth was spherical. It's kind of and you can go to the next slide there. One of the things, though, that he taught, though, was that the Earth was the center of the universe. And I don't blame them, because if you look up at the stars at night and you trace where the stars are going, you're going to see them moving around. And it kind of looks like all the stars are moving around us. And so I don't blame them for thinking that the Earth was the center of the universe, because that's kind of what it looks like. The other thing that they had going against them was living in a Christian part of the world. They believed in the Holy Bible. And I'm not going to get into discussion whether the Holy Bible is correct or not. I read the Holy Bible. I like it. However, the Holy Bible is not the best thing for science, right? There are some scriptures in there that kind of make it sound like the Earth is the center of the universe. And that is absolutely not true, right? However, these models persisted for hundreds and hundreds of years, and it was kind of difficult to think outside of that, because one, you have the Bible basically telling you Earth is the center of the universe, and then you have people like Ptolemy who taught that it was at the center of the universe. And then if you could go to the next slide there. So Ptolemy, we were talking about 100 AD, right? That's almost 2,000 years ago. So in science, most people thought that in the European world that the Earth was the center of the universe, up until this guy, Nicholas Copernicus. And that wasn't until 1500s. So we're talking about 1,500 years later almost, that somebody actually had proof to say, hey, look, guys, we're not the center of the universe. Nicholas Copernicus, he taught that okay, so I had a question here. Did they know at the time that the Earth rotated on its axis? And I'll get to that in just a minute here. Let's see. Yeah, so back then, what they were thinking about as far as the Earth was that they did not think the Earth spun. They thought the Earth was completely still, and that everything else rotated around it. So that's a really good question, because it's counterintuitive to think that the Earth is spinning. A lot of people thought, well, if the Earth is spinning, then we are gonna all fly off, right? And it doesn't feel like we're spinning. And so a lot of people thought that the Earth was still and that everything else moved around it. Yeah, so that's a really great question there. So Nicholas Copernicus, in his time, talked about what this model was called is the heliocentric model, that our solar system, that all the planets went around the sun. And he had a lot of evidence that this was happening. There was a lot of weird phenomenon that people had to try to explain. So for example, when planets are going around the sun, certain orbits are quicker than others. And so Earth will sometimes pass, kind of like a race around the sun. Earth will sometimes pass other planets, which when observed from the Earth, when we look up there, it looks like the other planets are going backwards for a little bit. And so it's kind of confusing. You see planets going around on a certain orbit, but then they go backwards just for a little bit. and then they go back forward. And so this was really hard to explain in what we called the geocentric model, where the Earth was at the center of the solar system. And so Nicholas Copernicus was one of the few in the Western world to be able to describe, hey, no, we're looking at it completely wrong. The sun's at the center, and the whole reason that we're seeing these planets go backwards is because we're just passing them. That's all. And that was a very simple explanation. But the thing with at the time is the government used the Bible for laws. And so they had a government and religion that was basically combined. And he received a lot of scrutiny and a lot of problems. They said, oh, no, you're crazy. You're trying to go against the Bible. And what Nicholas Copernicus said was, no, I believe in the Bible. I do. But I observed something different. And he was doing real science. He was actually observing what was going on. Now, when the planets would go backwards, they called these epicycles at the time. And even though Nicholas Copernicus correctly understood that we were passing by these planets, he didn't fully understand gravity. And so he still did have some of these epicycles in his model. Epicycle doesn't really make sense because now we know gravity, that planets and moons go around something that's much higher mass. And with the epicycles, a planet would basically go around itself. So someone asks in the chat here, what's an epicycle? So basically it was a model to try to explain why it looked like the planets were moving backwards. Now we know we were just passing the other planets. And so when we pass another planet, it looks like in the sky it's going backwards, but it's not. It's relative. The planet's not going backwards, but it looks like it is. So an epicycle is when they thought the Earth was the center of the solar system, they tried to describe, okay, well, a planet must be going backwards because normally it orbits around the Earth, but just for a little bit of time, the planet is just going to orbit itself. So an epicycle would be one tiny orbit that it goes around itself, which doesn't really make sense. Why would it orbit itself just for, just for a few weeks or a month? So the epicycles are not actually real. That's just the model that they looked at to try to explain what they saw in the night sky. And if you go to the next slide there. So not too long after that. I guess one more thing. So when we see those planets going backwards, today we call that retrograde. So like a planet is going in retrograde, and all that means is if you mark that planet, that spot of the planet in the night sky, you're gonna see sometimes it appears to be going backwards, doing a little loop, and then going back on its normal orbit. But that's only because we're passing it. It's kind of interesting. A lot of I don't know about in India, but in the US, there's the study of astrology, which I do not believe in or study, but they talk a lot about retrogrades, and they think it's very mysterious, and how retrogrades basically determine who you're going to marry and if you're going to have luck or different things. So it's actually still an interesting part of philosophy today, but it's not science. So, all right. So not too long after Nicholas Copernicus put this out to the world and saying, hey, we are not the center of the universe, and we are definitely not the center of the solar system. Johannes Kepler in 1609, he came up with mathematical equations to actually show what Nicholas Copernicus was talking about. Because Nicholas Copernicus, his math, did not completely work out. Like we talked about before, he had some errors in his ideas, such as epicycles. He thought that epicycles still happened, or that, in other words, that planets would occasionally rotate around themselves, which doesn't quite make sense. So Kepler, also known for his Kepler's 3 laws of planetary motion, he was able to actually use mathematics to describe the orbits of all the planets that were currently visible at the time. He also, in his first law, he showed that planets have an elliptical orbit, and this completely went against all other models. Even Nicholas Copernicus thought that the orbits of planets were circular, and so an ellipse, of course, is just a circle that's been flattened, right? And so planets do go in elliptical orbits, and that's a pretty important part of the equation, because what that means is when planets get closer to the sun, their orbit actually speeds up, and when they're much further away from the sun, their orbital speed actually slows down. If we had perfectly spherical orbits, we would expect, assuming it had a constant radius, we would expect the same speed of orbit, which is not what we see in the night sky. Absolutely. So Johannes Kepler had these wonderful equations, and they worked. They were able to predict where a planet was going to be in a year from now. So he published those equations in 1609, and then just 1 year later, if you could go to the next slide, just 1 year later, Galilei created a telescope. He basically reverse engineered a telescope. He saw the idea of a little scope that is used in sailing, and he was able to invent his own telescope and then pointed it to the stars. Of course, he was fascinated with that, and he discovered 4 moons going around Jupiter. Now, Jupiter has many more than 4 moons, but those are the biggest moons, known now as the Galilean moons. And he saw that something was orbiting around Jupiter. This completely went against what was taught before, that the Earth is the only thing that has planets or moons going around it. Nothing else in the universe does. But here he had proof that something revolves around something else, which completely went against their current understanding of the Bible. And but he had proof. Now, he probably would have been killed for his discoveries, because the government was so entrenched in the Bible at that time that they said, this is heresy. These are lies. This goes against God, and you cannot be telling about this. But he was friends with people in the Catholic Church, and so he was not killed. He definitely was punished. And in fact, he spent the last years of his life on house arrest, where he continued looking up at the sky and continued his study of the universe. Let's see here. So Galileo is pretty famously known for, in Italy, and the Leaning Tower of Pisa, dropping off things at the very top to show that things, that when things fall, when objects fall, they do not fall dependent on their mass. And he actually did conduct these experiments as a professor there, and he taught his students about this. And it was a pretty great experiment, because up until this point, most people thought when they're thinking of gravity, they thought that the heavier the object, the faster it would fall. And this is actually rooted all the way back. We were talking about BC, right? A couple thousand years ago, with Aristotle. He also taught these things, that the heavier a thing is, the faster it will fall to the earth. Now that's not true. Now it is true if it's on a hill, right? If it's on a hill, but if it's just a free fall, something falling in the air, free fall, going straight down, It doesn't matter how heavy it is not going to accelerate faster. It's not going to fall at a higher velocity simply because it's bigger. And so he showed that it has to do more with air resistance and buoyancy. So for example, if I dropped a balloon that had helium in it, it's not going to fall down, it's going to go up. So that's one example of extreme buoyancy, but buoyancy has to do with it, and then air resistance. So this research that Galileo did had a huge impact on gravitational research. And what's kind of interesting is the same year Galileo died, Isaac Newton was born. So I don't know. There's some scientists that believe in reincarnation. But even if you don't believe in reincarnation, it's kind of an interesting idea that two really great scientists, one died and then the other one was born in the same year. It's just kind of a funny thing we talk about in gravity. But either way, Isaac Newton, he probably changed gravitational research more than anyone that I know of, in the history of gravity. He did not blindly accept what people taught them. The textbooks of his time had all sorts of different, and you can switch the slide. There's all sorts of different errors in the textbooks of his time, what teachers taught, and he was very meticulous. He said, no, I'm going to go out and try to figure this out myself. I'm going to go learn this. And he spent so many hours of his day, every day, for years and years experimenting. And he never got married, and he was very proud of this. He said, no, I am a scientist. I'm going to study. I don't have time for any of this other stuff. I just need to learn. And he found that a lot of the things being taught about physics at the time were incorrect. He, in 1687, he published a book called Principia, and it had different laws of motions. Now, he studied Kepler's 3 planetary laws. And he derived these laws, basically used the same Kepler's 3 laws. He said, okay, these work, these are true laws, but he adapted them. And he was able to use those laws to be able to basically reverse engineer them to figure out the mass of other planets, of moons. If you can figure out basically how fast a planet is moving, and the distance between the two, if you can figure out that distance, you can figure out the mass of our moon, of other planets, of the sun, all sorts of things. And it took him many years to actually publish his research on gravity because his equations did not work on the moon. And the reason they did not work on the moon was because at that time, we did not have the correct distance between the Earth and the moon. It was way off. And so he thought, well, maybe these equations don't work. Newton once wrote, he said, Plato is my friend. Is a Greek philosopher. So Plato is my friend, Aristotle is my friend, but my greatest friend is the truth. And I think that's a great way to look at science, because even these days, we may think we're ultra modern, and we may think sometimes we know everything, right? But we don't know everything. Science is just beginning. There's so much more to learn, and there's a lot more truths to be found. So I think going through and saying, hey, you know what? Even though, like today, even though we think we understand gravity, we might want to test it just to make sure, or look at it in different ways, because there's maybe a lot more things that we can learn about now. Galileo and Newton both used these thought experiments about a cannonball. Newton used a cannonball experiment where you put a cannon on top of a really tall tower on Earth, and you shoot the cannonball. And Isaac Newton was able to calculate what speed would this cannon would this cannonball have to go to leave Earth's gravitational field. And so what he calculated was escape velocity. And that escape velocity we use to launch rockets. So he was very ahead of his time. He was absolutely a genius. And these, we still use Newton's equations in basic physics classes today to calculate all sorts of things at NASA, to all sorts of different fields of physics. However, there's a problem. Even though he was a genius, even though he was correct, his equations, if we try to, let me step back. So the way you can tell if a scientific model is correct is because it will predict things. So if his model is 100% correct, it could predict exactly where all the planets are going to be in 1 year, in 10 years, in 100 years, in 1,000 years. It wouldn't matter when. They would be able to predict that, right? That's the proof of how good a scientific model works, is its power to predict. So even though Newton's equations can predict all sorts of things here on Earth, when you throw something, you drop something, it was not able to predict the orbits of several planets within our own solar system. So for example, with Neptune, when they were looking for Neptune, they weren't able to find it because those equations, it didn't work. It didn't work for Uranus. It didn't work for Mercury. And the big thing for him was Mercury, because we can see, they were able to see Mercury at that time, and the equations did not predict where it was going to be in 6 months, in a year. So something was wrong. And that's another reason why it took Newton so long to publish his universal law of gravitation. So someone's asking if Neptune was found mathematically. So basically what happened when so later in time, much later in time, they were looking for additional planets, because even Newton's laws suggest that, hey, there's got to be more mass out there in the solar system. There's got to be something beyond Jupiter and Saturn. And so looking for Uranus and Neptune, Newton's laws wouldn't work. They say, okay, well, if we use Newton's laws, this is exactly where we're going to look in this same orbit. And if we search this orbit, we're going to find it. But they couldn't. They absolutely couldn't find it. But one day, they were able to find Uranus. There was a gentleman there doing a sky chart. And so basically what that is they make a map of every single point of light that they see in the sky. And then a week later, they'll make another, or maybe a month later, they make another map of every single light in the sky. And they're able to see, one of these points of light is moving. And so that's like, okay, well, that's probably a planet then, right? Because the stars appear to all move together, but planets will be moving in a different orbit. They'll be, and so once Uranus was discovered, they were able to say, you know what? It almost follows Newton's equations, almost, but there's about this, 40% error. And so they knew that there should be another planet beyond Uranus. And so they applied that error. They said, okay, well, if this equations were about, 30 or 40% off, let's apply that same error rate in Newton's equations to try to find Neptune. And guess what? That the same day that those equations were modified for that error, they immediately found it. So within 24 hours, they were able to find it. And so a lot of people thought, well, was Newton completely wrong then? Because there's this huge error in there. And it's not that Newton was necessarily wrong. It's just that we needed something different to describe orbits. His equations work perfectly on so many things throughout the universe. But orbits, it wasn't working. We needed some kind of adjustment or something to replace it. And that's where Albert Einstein came in. in the 1900s, in the early 1900s, he produced something called relativity, the special, and the general. Now, you all have probably heard of special relativity and time travel and light, speed of light, and it took him about 1 year to be able to derive those equations. But it took him almost after he figured that out, he was working on the general theory of relativity, and that has to do with gravity. And that's the part that we'll talk about today. But that took him an additional 10 years to be able to figure out the general theory of relativity. Still a genius, but it was a lot of work to be able to figure out how objects work in space-time. So you can switch to the next slide. So Albert Einstein, he looked at gravity a lot differently than everyone else. Some people back in Aristotle's time, they talked about an ether. They said that between planets, there's a great ether, this great mysterious matter between planets. And in Newton's time and beyond, they were like, no, it's empty space. It's completely empty space. There's nothing there. But in a way, Albert Einstein actually brought back that ether in a way by calling it space-time. And I think the big difference with the general theory of relativity is it doesn't even call gravity a force. Right now, we know of 4 forces in the universe. We know of electromagnetism, gravity, and then the weak nuclear force and the strong nuclear force. Back in Albert Einstein's day, when he was initially working on the general theory of relativity, they only knew of 2 forces in the universe. In modern physics, they only knew of gravity and electromagnetism. And in the general theory of relativity, it looks more of space and time as one thing, and how the sun, if the sun is very massive, it's bending space-time. And in his equations, it showed that's the reason why Earth is going around the sun, is because the sun has so much mass that it bends space-time so much, kind of like a trampoline. Something really massive on a trampoline, and where planets and moons are basically falling into that bent space-time. And so this was a very, very different way to look at gravity and to look at the universe. What they thought was kind of a problem though at the time was, if this was true, you would have what is called singularities. And a singularity, there's kind of a few different definitions or ways to look at it, but one way is just infinite densities. Or in other words, let's even just take one apple. If you had one apple and it took up, and if your volume was 0, if you had an apple and your volume was 0, then it would have an infinite density, because density is based off of how much volume it occupies, right? But if it's by 0, then you have an infinite density. And so you have these different things like black holes. And at Albert Einstein's time, they had never viewed a black hole before. They haven't seen one before. But one consequence of general relativity would mean that black holes would have to exist. And at that time, it would, let's see here. Yeah, at that time, because I guess I'll step back here. So one thing with science is a lot of times you have theoretical models that come first, but then later is when you have the evidence. And so, Einstein had these ideas, and then a few years later, they were actually able to put general theory of relativity to the test. And one of the way that they did that was during a solar eclipse. Now, the moon blocked the sun, and then the light bends around the moon, and they were able to calculate if the general theory of relativity was correct. They had said, all right, this is how much light would bend around the moon. And that experiment was met with great success. It correctly predicted that. Now there's been several experiments since then, and the way that we look at general theory of relativity is right now, that is the best way to describe gravity. We've had so many tests done on this, and it works. It absolutely works. But we have to be critical of theories. One, because if there are some errors in it, then we can learn something. From that. For example, just like Isaac Newton's universal law of gravitation, there was some errors in it, and we need to modify it and change it over time. Now, am I saying we have to modify the general theory of relativity? Well, maybe, maybe not. Time will tell on that. But there is something interesting in nuclear physics and subatomic physics that's going on right now. We have what's considered the greatest model of physics, and it's called quantum mechanics. Now, I'm sure you all are probably familiar with quantum mechanics, but basically, it's the principles that govern things that are smaller than an atom. So an electron is a part of an atom, but an electron is smaller than an atom. And so there's all sorts of different things that happen on these scales. One of those is called superposition, which means something can occupy two different spaces at once. I don't know if you all have heard of the double slit experiment, but basically you have two little slits and you shoot electrons. And you would imagine if you shoot a bunch of little electrons through these little slits, they would come out on the other side and you would detect two lines. However, what we actually detect, and this experiment has been done thousands and thousands of times, what you actually see is you see an interference pattern. And this interference pattern is just like if you took two rocks on a pond, drop them, and you have the waves intercept each other. And you see this interference pattern. And so that's kind of changed our way that we look at subatomic particles. Sometimes they behave like particles, and sometimes they act like a wave. And this is called particle-wave duality. They exhibit both of these. There are many strange phenomena that occur from the principles of quantum mechanics. The more we know about a particle's position, the less we know about its energy and its direction and its state. And Albert Einstein did not readily accept quantum mechanics. What he said was, God does not play with dice. Or in other words, basically saying that, no, physics needs to be sure. It needs to be, we calculate something precisely. We need to know exactly where it is and its energy state at the same time. Yeah, and so someone in the chat put the Heisenberg, talking about the uncertainty principle. Exactly. And so what Einstein actually did for his last 30 years of life is he tried to reconcile the two known forces in the universe. So like I said before, it was gravity and electromagnetism. He didn't know about the weak or nuclear force when he initially started this endeavor. And he initially rejected quantum mechanics to try to include that into the equations. So he tried to reconcile these two forces. And what I mean by reconcile is if 1 + 1 = 2 over here, then 1 + 1 should equal 2 on Pluto or on Uranus or in another galaxy, right? If it's the laws of physics that are correct, they should work together. And so if gravity is correct and electromagnetism is correct, then we should be able to mathematically combine them somehow. And that's what his ideas was. He spent the last 30 years of his life trying to reconcile those two, and he was not able to do it. Kind of back to quantum mechanics is when we look at subatomic particles, they do not react the same way when we're talking about gravity. They don't react the same way that they do like in the big world, in the macroscopic world. And one example of this is if we go back to that double slit experiment, where we're shooting these tiny subatomic particles through these two slits. Now, a particle may actually be going through both slits at the same time, one particle. And that's a weird phenomenon we don't see on this big world. But of course, once we detect it and once we measure it, the particle almost decides and chooses, okay, I'm going to be going through this slit. What's weird is in these two slits in the double slit experiment, once we basically take a picture, once we snapshot that and freeze that and actually take a measurement, what we see is one particle. So let's just talk about one particle. So one particle, we see, okay, it went through the right slit. Cool. But what's weird is its gravitational force, its gravity, instead of going through the right slit, it went through the left slit. And so this is a very confusing principle with quantum mechanics when we're trying to talk about gravity. It doesn't make sense. If the particle goes through the right side, its gravity should follow it. Its gravity should be with it, right? Because we know on the macroscopic scale and on the general theory of relativity that the reason it has a gravitational field is because the particle or object is bending space-time, right? But in quantum mechanics, we have this disparity. We have, sometimes you'll have the gravitational force go to the left, while the particle goes to the right. And so the whole reason that we have newer models to try to explain gravity is because we want to try to reconcile this problem. We think in particle physics that this is a problem, but it may be that my research and the other people's research in quantum gravity, it may be that this is all in vain. We may be trying to fix a problem that doesn't exist. And so we have to, even though quantum gravity is the cutting edge research in physics right now, we have to realize, hey, we might have our ladder put up against the wrong house. We may be trying to fix a problem that doesn't actually exist. Maybe gravity and the other forces were never meant to be reconciled. But nevertheless, as of right now, we do not know. And so there are many people that are trying to reconcile gravity with the other forces. Now, I will tell you, quantum mechanics, like we said, is one of the most well-tested models there is. It has combined 3 out of the 4 known forces in the universe. So mathematically, it's been able to combine the strong nuclear force, weak nuclear force, and electromagnetism in a beautiful series of equations. However, it has not been able to incorporate gravity. There's been many people that have tried. There's a physicist, and you can go to the next slide there. So this is space-time bending. You can kind of see that's Einstein's model. As the Earth is heavy, has a lot of mass, it bends the space-time around it. And the moon is basically falling towards it. And then you can go to the next slide. All right, so this is one very important part of gravitational research. It's one of the experiments that we can use to test different gravitational models. This is called the bullet cluster. So the bullet cluster. So many different galaxies come in clusters, galaxy clusters, and we see that throughout the universe. Now, what's really interesting about galaxy clusters is that we see them together. We look at this group of galaxies over here, over there. We typically find them in a cluster. And we ourselves, the Milky Way galaxy, is currently in the Virgo supercluster. We're in a group of other galaxies. Andromeda is one of them, and there's several other smaller galaxies that are in our little group. But if you use the general theory of relativity, or you use Isaac Newton's universal law of gravitation, it doesn't matter. Either model that you use, if you count up the mass of every single star in the galaxy, and you add up all of those, there is not enough gravity to keep clusters together. And so this is one of the other problems that we have in modern astronomy, is what is keeping all of these galaxies together? there's not enough gravity as we know it to hold it together. So what that means is either our understanding of gravity is wrong at large scales, which that might be true. Maybe we need to revise the general theory of relativity. It doesn't seem like we need to revise it because it seems pretty perfect. But so it's either our understanding is wrong, or there is some other mass that we can't see right now that's there. And what we're calling it right now is dark matter. And so dark matter is a really important field of research right now. And if it exists, basically it's just a type of matter that does not interact with the electromagnetic spectrum. So we can't see, we can't shine a light on it and show it, and it doesn't emit any light. But this dark matter, if it exists there, is what is keeping the galaxy clusters together. Now, if this is true, in many instances, more than 50% of the matter within a galaxy cluster would need to be this mysterious dark matter. In some cases, it would need to be over 80% of the mass in the galaxy cluster would need to be dark matter. So it's kind of a big claim to say, hey, yeah, all of this, everything that's keeping this thing together is this mysterious thing that we don't know about. But what's interesting about this picture here, the bullet cluster, is when they look at the gravitational force, you expect the gravitational force to be where the normal mass is, right? You'd expect it to be near the big stars, right? Or where the big groups of stars are. But the gravitational force is not there. It's actually surrounding the bullet cluster. And so that gives a lot more evidence that, yeah, there is a really good chance that there is this dark matter, because the gravitational force is not happening from where the groups of stars are, but actually kind of in a halo or in other parts surrounding the clusters where we wouldn't expect a strong gravitational force to be. There are several different models, gravitational models right now, that say, no, dark matter does not exist. Now, these are just models, right? And so we don't know for sure which model is correct yet, but we do know which ones are probably wrong. One of the models that says there's no dark matter out in the universe is called modified Newtonian dynamics, and they call that MOND, so MOND for short. And what this says is basically there's no dark matter, but our understanding of gravity is wrong at large scales. And that's a pretty attractive idea that we should look into, right? I mean, maybe our understanding of gravity is wrong, right? I'm not discounting that part at all. But specifically, I am discounting specifically MOND because its equations do not work in all circumstances. And then the other part is that we have found some galaxy clusters that don't have any dark matter. Or in other words, there are some galaxy clusters that, because there's no dark matter, they are breaking apart. And they don't have this weird center of gravity or this weird gravitational force in different places than we'd expect it. Like the bullet cluster, for example. We look at some of these clusters and we see, okay, their gravity is in the normal spot. That's where we would expect it to be according to general theory of relativity. And oh, look, these clusters are starting to break apart. And that makes sense, right? If you don't have enough gravitational force, things are going to break apart over time in space. So there's several different models that try to challenge the general theory of relativity, or some of them even just add to it. We've had so many advances just in these last couple hundred years of our understanding of the four forces. Who's to say that in the next 200, 300 years, we're not going to have even bigger advances? There's so much learning to be had in science, and we do not have it all figured out. So MOND is one of those that challenges it, and I'll go through just a couple other ones. I'm not really a big fan of MOND. I think there's a lot of experimental problems with it. But there is the best version of MOND takes into account the general theory of relativity, and they call that relativistic MOND. And that actually has worked Not in everything, but it has worked on several experiments. The kind of weird thing, though, with relativistic MOND is that it does not discount dark matter completely. And what they call it is dark dust. And so in their model, there is still a little bit of dark matter, but just not 50% dark matter or 70% dark matter in these circumstances. So this model still says, yes, our understanding of gravity is wrong at large scales, but there is some dark matter basically in the universe. Could you go to the next slide? So our next model is called chameleon theory. Chameleon theory, and as you're probably familiar with the animal chameleons, they can change color over time, right? And chameleon theory basically says that the reason we're having these different things that we see in the universe happen, these weird things happen, it's not because of dark matter, and maybe it's not even because our understanding of gravity is wrong, but the reason is because right now we only know of 4 forces, but chameleon theory says there's actually a 5th force that we don't know about, that we're just discovering, which may be true, may not be true. This 5th force, they believe, is present through the chameleon particle. And this would be an alternative to dark energy. Now, dark energy, as you probably know, is very different than dark matter. Dark matter is actual matter, right? It just sits there and creates a gravitational force. Now, dark energy is what basically Einstein called his biggest blunder. You probably remember that it was lambda in his equation, or also known now as the cosmological constant. Basically, Einstein did not know if the universe was expanding or contracting. He actually believed that the universe was steady and was constant, that it was not expanding or contracting. And so when Mr. Hubble, with his telescope, provided sufficient evidence that the universe was not just expanding but accelerating, Einstein's, what he called his biggest blunder or mistake, is actually correct. You do need part of a mathematical model to show the expansion of the universe. And so he thought he messed up in his equations, but actually Einstein was correct all along, and he just didn't realize it. And so anyway, what we call this, you would need to have something to accelerate the expansion of the universe. You know, most astronomers believe in the Big Bang, that the universe started at a single point and accelerated. But eventually the universe would start to slow down, right? I mean, we don't know of energy just coming from nothing. And so now that we see that the universe is not just expanding, but it's accelerating in its expansion, we need to figure out, why is this accelerating? There has to be some force or something pushing it. Now, chameleon theory says that the reason for the expansion is these chameleon particles, and it's this 5th force. Or in other words, you know, what we mostly call it today is dark energy, or the cosmological constant. And we still do not have a consensus around the scientific community as to exactly what's driving it. Yeah, we're calling it dark energy right now, but what is dark energy, and why is it there? For example, I remember earlier in the, okay, so someone's asking about inflation, and so inflation, and I assume you're talking about the inflation of the universe, and that's exactly what I'm talking about. Is the universe is expanding, so, or in other words, the space between galaxies is stretching, and so that is inflation. That the universe is inflating, and we can see that very, very clearly, that it's inflating, it's expanding. Now, over the next several thousand years of us here on Earth, we're not going to notice that between us and Mercury, or us and the sun. That's not where this expansion is taking place. It'd be more in between galaxies. So don't worry, we're not going to get too far from the sun or something like that in the next, 50,000 years, 100,000 years. We don't have to worry about that at all. Some of the other models, I remember somebody earlier in the chat asked about a graviton, and so this is where we'll talk about that. One of the gravitational models that challenges general relativity is called massive gravity. And so basically what that is saying is that just like if you think about the electromagnetic spectrum, or sorry, the electromagnetic force, that force is carried throughout the electron, right? When we plug in our computer into the wall, electrons are flowing to power that, right? So the electromagnetic force uses the electron to carry its force. Well, massive gravity asserts that gravity is carried, kind of like the electron, gravity is carried by what's called a graviton. Now, this may or may not be true. We have not detected a single graviton. When we look at gravity, gravity is the weakest force by far. It is so weak compared to the other three known forces. And so to detect a few gravitons would be extremely difficult. Research and experiments right now are trying to detect trillions and trillions and trillions of gravitons. We have not been able to successfully detect them yet, but they may exist. One of the things, though, that's kind of interesting with massive gravity and with other theories like this that purport to have a graviton is that a lot of graviton theories say that graviton would have mass. Now, in reality, if a graviton exists, it could be massless. And when I say massless, like a rest mass of 0. Like, for example, a photon has a rest mass of 0. And so it's possible that a graviton has a zero mass at rest. And the reason we say at rest is because with the special theory of relativity, as things speed up, they can change in their mass, basically. But anyway, so if a graviton exists, it could be massless or it could have a mass, but most gravitational theories that talk about a graviton say a graviton has a little bit of mass. There's problems with this, because if a graviton were to be detected, it would mean that it would be going slower than the speed of light, right? Because if it has mass, then we know things with, the special theory of relativity says that things with mass cannot travel at the speed of light. They cannot. So where this kind of goes to LIGO, L-I-G-O, is for the last half decade, we've been detecting gravitational waves. And so one of the first big events was two black holes merged together. They crashed together. And if gravitational waves exist, according to the general theory of relativity, they would warp space-time. They would bend space-time significantly. Just like if you dropped a rock on a pond, it would cause the water to ripple. So that's what we're looking for. And in fact, when those two black holes merged and crashed together violently, we were able to detect gravitational waves. The wave came through our Earth and actually stretched our Earth slightly, and we were able to detect that. Now, the problem with gravitons is if gravitons have mass, then that would mean that the gravitational waves would be going slower than the speed of light. However, when we measure gravitational waves, they do go at the speed of light. So there's problems for a lot of models that challenge general theory of relativity with that. I know we're almost out of time here. I'll go to string theory here. So could you go to the next slide? So there's a picture of what gravitational waves could look like. And the reason I threw this in here is because the pond idea is when you drop a rock on a pond, we think of gravitational waves in 2 dimensions, but gravitational waves are not in 2 dimensions. They would be going in 4 dimensions and in all directions, including time. And then can you go to the next slide? So this is called the standard model. So if anyone studied physics, you're very familiar with the standard model. And most standard model pictures do not have the graviton on it. But this one on the top right, you can see has the graviton. And in big letters, though, it has hypothetical. So if we find it, that's where it's going to be. It's absolutely possible, though. We had the Higgs particle on there in some models, and we eventually found it, right? So there's definitely a high possibility it's there, but there's a good chance it would be massless if we do find it. And could you go to the next slide? So this is Richard Feynman. He won a Nobel Prize on his research for combining quantum mechanics with electromagnetism. And so he spent some time trying to use the same principles that he did to combine quantum mechanics with gravity. And this is the whole reason for quantum gravity. We call it quantum gravity, but this is the whole reason for quantum gravity research, is to combine the forces. If 1 + 1 = 2 over here, shouldn't it equal to, on the small scales? So he tried to reconcile, and if he was able to be successful, what it would have been called is the theory of everything. What this means is we would have been able to combine all 4 known forces in the universe, general theory of relativity, and quantum mechanics into one set of beautiful equations. Unfortunately, he was not successful in being able to combine these. Can you go to the next slide? So we have several different models trying to create a theory of everything. And what this would do is it would reconcile why in the double slit experiment, the particle goes to the right, but the gravitational force goes to the left. One model is called string theory. Now we've had many different models of string theory. And so today, what we call it is actually M theory. M theory takes into account all the best parts of the different string theory models. But M theory is string theory model. It's just the best of the best there. And in 1995 is when the M theory was kind of reconciled with all the different parts. And its biggest enemy or opponent to string theory is loop quantum gravity. So, and I'll explain the differences here. So M theory has all the forces together. It reconciles quantum mechanics and general theory of relativity. It does a great job mathematically. There are it's complex. It's overly complex in the way they do it, but it works. Mathematically, it works. However, if this model is correct, what it would mean is that there are 11 dimensions, which is okay. I mean, we know of 4 dimensions right now. There may be additional dimensions out there. When Einstein was trying to reconcile electromagnetism and gravity, remember that? In that model, he had a 5th dimension. He required a 5th dimension for that model to be able to work. And he called that a 5th curled dimension, meaning the 5th spatial dimension. Right now we have 3 spatial dimensions we know of, but in his model, the 5th spatial dimension was curled, or in other words, kind of hard to see, difficult to see, because it took up a very tiny space. Now, if this is correct, we will eventually be able to detect the 5th dimensions through the 11 dimensions. In this model, there's still only 1 dimension of time, but these other spatial dimensions, we will be able to either prove this model correct or incorrect. Absolutely. Its opponent, loop quantum gravity, says that there's no additional dimensions and there is no supersymmetry. Supersymmetry is a very important fundamental part of the string theory model. Now, supersymmetry is that basically when the Big Bang happened, all the particles that we know of today had opposite partner particles that existed. And so if supersymmetry exists, we would be able to find all of these partner particles. And if we can't find them, sorry string theory and sorry M theory, but it's not gonna hold up. String theory has had a lot of criticism over the years, and it's gone up and down in popularity in the physics community. But the big thing is we need better ways to be able to test it. It's extremely difficult to detect other dimensions with us just knowing about these 4 dimensions. But what's interesting is mathematically, there may be many dimensions that exist in the universe. We could have 5, we could have 11 dimensions, we could even have more. And even if string theory is not right, these ideas, we should test these. We want to know if there's additional dimensions. We want to know if there's a graviton. And if there is a graviton, we want to know if it has mass. We want to know, even if all of these other models are wrong completely, we want to know if there's a 5th force. This type of research will help us to better understand dark matter and also dark energy. And so, yeah, there's many other models that newer models that talk about that try to explain gravity, and more specifically try to explain quantum gravity. And I hope that one day we're able to figure out a quantum gravity equation, but like I said before, it might not exist. But I know that the research in this field will definitely help us to find out more about those things we talked about: dark energy, dark matter, other dimensions, other forces. And I'm just really grateful to have a very, very tiny part in this research. So I've already gone over time. Did we have any more time for questions? But that's all I had.
That was a really informative session, sir. So thank you for that. And the link has been presented in the chat message already. So it would be requested for everyone to kindly go through it. Just a minute. Right. So the link for the form to be filled, the feedback form, has already been shared on the chat message. So for those who wish to see their certificates and acquire it, kindly do fill the form. And so we would like to extend a very warm thank you to Mr. Oslapas for accepting our invitation and spending his precious time sharing his experiences and knowledge with us. We're very grateful for that. And thank you for being an amazing audience with curious minds. And that's it from our side. So goodbye and have a great evening. Thank you, everyone.
Thank you.